Okay, hello everyone and welcome to the afternoon session of the first day. So our speaker today is Stefan Weltge, who will speak on lattice-free simplices of lattice widths better than twice d. Please, Stefan, the floor is yours.
Thanks a lot. Thanks a lot for having me. Thanks a lot for giving me the opportunity to talk about some recent joint work with Lukas Meyerhofer and Yamiko Schade, who are both PhD students at the Technical University of Munich. And yes, so this is about, so for the experts, what we do is we construct lattice-free simplices whose lattice width is 2 times the dimension minus something little o of d. Okay, so in fact, you will see several objects that Daniel introduced in this talk today, but don't worry, I will repeat everything. Actually, I keep everything in a self-contained way, and I try to keep things very simple. Okay, good. So let's start with a very few basic definitions. So first of all, lattice-free objects, we had them this morning. A convex body is lattice-free if it does not contain any integer point in its interior. Okay, so here, in fact, everything is with respect to the standard integer lattice. Okay, don't worry about the dual lattice. Don't worry about anything else. It's just the integer lattice. Okay, and convex body means that it's a convex set, closed, compact, and full dimensional. Good. Then one notion that we also saw this morning, I think Daniel just called it the width. Let me here call it the lattice width to be more specific. Again, everything with respect to the integer lattice is the following. You take any convex body K, okay? And now the lattice width somehow corresponds to lattice hyperplanes, like parallel lattice hyperplanes. And you basically count the number of shifts that you need to cover your body or the integer points in your body. Formally, it is the following, okay? You go over, so I call it LW of K, lattice width, okay? So you go over all integer vectors that are non-zero. So that's my objective. So in this picture, that's this guy here. Okay, you go over all of them, and then you compute the maximum of C transpose X over K and the minimum, and you take the difference, okay? So it's like this width, okay? And now you search for one integer vector for which this difference here is small as possible. Okay, and of course you exclude the zero vector. So sometimes this is confusing to people. So this is not like the Euclidean width with respect to that vector. Okay, you don't rescale that vector anywhere. Okay, in fact, it more like corresponds to really counting these lattice hyperplanes. So for instance, if this is your convex body, if this is your direction, let's say it's the 1, 1 vector. Okay, then the width will be a bit more than 2. Okay, a bit more than 2. Good. By the way, I don't see you. Whenever you have a question, just interrupt me. Good. Now, one of my most favorite theorems in that area concerning lattices is the so-called Flatness theorem by Khinchin, which was first proved by Khinchin in 1948. And it states that if you have a lattice-free convex body, it will be flat. And it will be flat with respect to the lattice. And the formal statement is the following. For every dimension, there is a finite number, FLT of D, which we usually call the flatness constant. Okay, or the flatness constant is the smallest number that satisfies the following, such that whenever you have a d-dimensional lattice-free convex body, its lattice width will be at most that number. Okay, so the maximum lattice width is finite for fixed dimension. And we have seen this morning already that this statement here has some applications in integer programming. Actually, it has many more applications, not only for these very direct algorithms for integer programming, but also in terms of cutting plane theory, you see that, or also on the complexity of integer programming formulations. This fact is used several times, a lot of times actually. Good. What do we know about this? Most work has gone into proving upper bounds, of course, for obvious reasons on this flatness constant, beginning by Khinchin, and then we heard about the work by Kanan and Lovash. Banashik and co-authors improved bounds a lot, and the best bound is due to the work of Rudolfsson. which is the flatness constant is at most d to the 4/3 times some polylogarithmic terms. Okay, and as Daniel mentioned, the conjecture is actually that the flatness constant should be linear in D. Okay, or maybe super close to linear. Good. However, in this work today, I don't want to focus on upper bounds. I would like to focus on lower bounds. So I would really like to understand, like, what are large lattice-free convex bodies, and large in terms, of course, in terms of lattice width. Okay. So what is known about this? It turns out that there's not really much known about this. Well, so let's go through the dimensions. Dimension 1 is trivial. You just take an interval of unit length. This is giving you the largest lattice-free set. So the flatness constant in dimension 1 is 1. Fortunately, we also know the flatness constant in dimension 2, which is this value. Okay. And it's 1.08 times d, where d is now, of course, 2. Right. And this is due to Horkins. And his example is a triangle which looks like this. Okay, so it has some integer points in the boundary. That's what you expect. And the lattice width is a bit more than 2. Okay, good. These two dimensions are the only two dimensions where we know the flatness constant. Okay, and not much is known about higher dimensions. One thing that Paco Santos and Giulia Codinotti recently came up with is a construction in dimension 3. So they obtain actually a 3-dimensional simplex of lattice width this 2 plus square root of 2, which is relative to the dimension a bit more than what you have here. It's 1.14 times the dimension. Okay. They actually conjecture that this is the flatness constant in dimension 3. What they have been able to prove together with Gennady Averkov and Makia was that this simplex here, this 3-dimensional simplex, is a local maximizer of the lattice width among lattice-free convex bodies, which means that whenever you have a lattice-free convex body that is sufficiently close to their simplex, it will have lattice width less or equal to this value. Okay. Good. And finally, I should say that there are some arguments which involve a direct sum, telling you that the flatness constant is super additive in the dimension. Okay, so essentially what this means is that basically you can lift these constructions to arbitrary high dimensions. Okay, so in some sense, this 1.14 times the dimension is state of the art. We don't know anything else. We didn't know anything else yet. So in terms of lower bounds. Good. But I mean, of course, if you see this, well, the best constructions, they come from very small dimension examples. I guess it's natural to wonder, I mean, what happens? Can we do a better construction dimension 4, 5, and so on? And that's what we worked on. Okay. So let's do that. Let's try to construct lattice-free convex bodies of larger lattice width. So there are 3 main difficulties. I mean, first of all, well, what are good constructions? It's not that we have a candidate in mind. We don't know about a good candidate yet. Okay, second is, well, if I have a candidate, I mean, I want to prove that it's lattice-free. But usually this is a very difficult question, right? I mean, all the algorithms that Daniel was talking about today, they have still exponential running time, right? So this is a difficult problem. Also, I mean, once I have that body, I mean, I want to prove that its lattice width is a certain value. And also this is usually difficult. Okay, let's not worry too much about these 2 points here. Let's first of all get some inspirations how we should construct such bodies. So what we do is, I mean, we don't know much, right? But let's look at the 2 previous examples a bit more carefully. Let's look at these local maximizers a bit more carefully. The first thing that you should do is, because they don't look super nice in the original ambient space, it helps if you lift these examples to this hyperplane H, which is just 1 dimension higher, and I look at all the points whose coordinate sum is equal to 1. And the way I lift things is very easy. I take the first coordinates, I leave them as they are, and the last coordinate is just 1 minus the sum of the previous coordinates. Okay, it turns out that if you lift it like this, these previous simplices, they have a nice pattern, they have a nice description. Okay, good. So first of all, what you realize, so take one of these maximizers. First of all, they are a simplex, good, that's what I already told you. But now they have the standard unit vectors, the first d plus 1 standard unit vectors, as integer points in their boundary, or in the relative boundary, if you want. Okay, good. Second, and now this is a crucial property. These simplices, they are like highly symmetric in some sense, in the following sense. The vertices of such a simplex, they are all cyclic shifts from each other, or of each other, okay? So what I mean is that there exists one vector, v, okay? So that all the other vectors, one vertex, v, so that all the other vertices are just cyclic shifts. So this thing here is the original vector v, where you permute the coordinates, you shift just all the coordinates cyclically by 1 unit, let's say. And here you continue. Okay, so it's all the same vector, just a cyclic shift. And you take the convex hull, and this is your simplex. Okay. As a consequence, you can also look at the inequality representation. And in the inequality representation, you will see the same thing. So basically, there is one vector A, okay, and this is the last entry of that vector, so that all the inequalities are, well, the normal vector of the inequalities is always the vector A, like cyclically shifted. Okay, good. And this is the notation that I want to keep. So V is always, so everything I need to describe such a simplex is this one vector V, right? And this one vector A. And this is what I will keep. V is the vertex, A is the normal vector.
Stefan?
Yeah?
But what is the right-hand side? Is that like A, D plus 1? Does that get cyclically shifted in any way? Or
No, this is this is really, yeah, you fix that vector, you take the last entry, and you can think of this as the largest entry if you want. This is, I mean, actually you can think of this as being 1. We will normalize it so that it's 1. But this is not shifted. It's always the same.
Okay.
Mm-hmm. Great. Good. Okay. I mean, let's do this, right? And let's do a search in this family, right? It seems to be at least a good idea in dimension 2 and 3. Okay. And that's in fact what we did. We did lots of computations. Don't ask me about details. It's like it's a bit hacky, but we can do a lot of computations in high dimensions. For instance, one thing that we can do is we can go to dimension 4 and 5. And we can compute lattice-free simplices whose lattice width are like these expressions, which are a bit ugly, unfortunately. But we can already improve like on let's say, the best bounds that were previously known. Okay. Actually, we can do something more, at least for dimension 4 and 5. We can also prove that these simplices are local maximizers. And not just within that family, but within the family of all lattice-free convex bodies. Okay. And you can continue. You can do computations also in higher dimensions, 6, 7, until 10. That's rather okay-ish. Okay, and you see that these ratios here relative to the dimension, they grow and grow. They get bigger and bigger. Okay, but of course, I mean, they should not become too big, because I mean, if we believe that the like flatness constant is linear in D, I mean, they should probably converge to something. Okay. Unfortunately, we're not able to get like algebraic nice expressions for dimension 6, 7, and so on. I mean, first of all, the pattern seems to be very difficult. We have some idea. I mean, it might correspond to some cosines and sines of some angles, natural angles, but also from dimension 6 on, like the combinatorics, with respect to the integer lattice, they seem to change a lot. So I think things become more difficult. Okay, so I cannot give you local maximizers in dimensions high. Okay, but still, let's go on. Let's try to push this value to something. Okay, and actually we can push it to something nice. So let's get some. I mean, we can do computations for higher dimensions. That's what I said. But we only get, like, let's say, approximate maximizers. Okay, at least within our family. So let's get some more inspiration from them, and then you see lots of nice patterns. So what you see here, for instance, is the following. For every dimension, I drew a graph. Okay, I drew a function. So maybe we look at the very last function, this very bottom thing here. So that's for dimension 10. So what you see here is I'm just plotting the coefficient vector A, right? So here's the first entry, the second entry, and so on. Yes, and what you observe is that, I mean, okay, yeah, it really feels like, man, there is a pattern, right? It's like some nice functions. It was very hard for us for several weeks or months actually to figure out what is that pattern actually. However, we get, I will get back to this, but we will get, I mean, is it a polynomial? Is it an exponential function? I don't know, right? But we get one inspiration from this, which is super helpful in this family, which is the following. I mean, you see they're all monotonically increasing. I mean, they are even convex, but I don't know how to use that convexity, but the monotonicity is super nice, because what you can prove, it's in the end, it's easy, is that if the coefficient vector is monotonically increasing or non-decreasing, okay, then if you define that simplex in the way I described it, you get a simplex that is indeed lattice-free. So once you just care about this, and it seems that you should care about this, right? You don't have to worry about lattice-freeness. It's automatically lattice-free. Good. Very nice. Let's look at the vertices of the guys we have computed, okay? It turns out that they follow a certain pattern. What you see is that the first entry, I mean, up to cyclic shift, of course, the first entry is always a very large positive number. And then you see several strange numbers in between that are all like rather close to zero. They are not entirely zero, and you should not set them to zero, but they are like wiggling around the zero. And then you have a very small, so I mean, very negative number, which is the last number. Okay, good. And so, I mean, if you have such a simplex defined by the convex hull of such vectors, I mean, what would be your bet? Like, what is the lattice width? Well, probably it's like, I mean, just maximize in the direction of a unit vector. So let's maximize just in the direction of that coordinate. So that guy will give you the maximum, and that guy with a minus will give you the minimum. So in other words, I mean, just let's simplify things, okay? If you have a vector that looks like this, so two positive numbers, p and q, right? You have plus p here, minus q here. Let's say the rest is zero, okay? We can still use that lemma later. If it looks like this, and you take the convex hull, as I described before, take all cyclic shifts, then you can actually prove that the resulting simplex has a lattice width that is equal to p plus q. Okay, so your guess is right. So that's also helpful, because this means that at this point, we do not have to worry too much about being lattice-free or what is the lattice width, as long as we have the vertices that are structured like this. Good. So what is the remaining problem? Well, I mean, right? What we do is we have to find a monotone coefficient vector A, monotone, so that's lattice-free, such that, I mean, let's hope that this value, like the first entry minus the last entry of the resulting vertex, is large, okay? And let's hope that the other entries are really small, because then we have control of the lattice width. And I said V, right? V is the vertex vector that arises from A. Okay, so how are they connected? Well, they are connected in a simple linear algebraic way, right? So you have, I mean, this vertex is tied at most of the inequalities. So all these inequalities are kind of this form, okay? And here for the right-hand side, I'm assuming that the last entry of A is 1, and maybe the first entry is equal to 0. Okay, so everything is between A and 0, and I can assume this. That's fine. Okay, and this is like this thing here is the equation, sum of the coordinates is equal to 1. Good. So now seems like a simple problem, right? I just have to find A and B so that, you know, they satisfy this, right? Unfortunately, this is, I don't know, we spend a lot of time finding out how to compute such, I mean, right? A and V are unknown, of course they are related, but it's not so easy to just directly solve that. That's why we took a somehow crazy approach, which I would like to share with you, because I found it fun. I mean, maybe there's a simpler way, but I doubt it a bit and I don't see it. Okay, maybe at that point, is it clear what we want to do? Or are there some questions I should ask like this? Okay, good. So let's do this. I mean, let's look at this system. From now on, you don't have to pay attention on all the details, but just try to get an idea, okay? So what we do is we take that original system and we look at this matrix here in the middle, and we call it C, okay? And we will also, I mean, the really interesting entries for us are V1 and Vt plus 1, so let's keep them. But let's call this vector here in the middle, let's just call it W. This is not going to be too interesting for us, right? Because we expect that maybe it's just consisting of tiny values. Good. If you do this, then your system looks like this, okay? You just split off everything, nothing happened here, and you still keep that first equation, which says sum of all the entries should be equal to 1. Good. And now, I mean, I'm also not really interested in V1 and Vd plus 1. I'm rather interested in the difference. So let's call this lambda. And actually, let's divide it by, yeah, for some random reason, let's divide it by 2 times d. Okay, so let's normalize it somehow. And remember that we want this lambda thing to be big. So if you do this, if you manipulate the constraints a little bit, you get a system that looks like this. Don't worry, like you don't have to look at all the details. Okay, it just looks like this. So we still want to find that vector A and W, and so that lambda satisfies this equation and so on. Good. This looks a bit crazy, but there's actually a reason why we do this. And this was some very nice insight by Lucas, actually. Because what we're doing is we take an infinite dimensional view on this problem, okay? So what we're doing is, instead of looking at this vector, like at A as a vector, we will treat it as a function, okay? So we will treat it as a function from the interval 0, 1, maybe, and we will call this function y, okay? And if you think about this as a function, now you can, I mean, now this step is not rigorous, okay? So this is not a very formal thing to do, but it gives us a good idea, okay? So because, I mean, what do we have here, right? I mean, if y is, let's say, a nicely behaving function, right, you would expect that a1 and a2 are essentially the same, a2 and a3 also, and so on. So what you see here is 2 times that function, but you divide it by a factor of 2, so you see your function here, okay? Also this thing, I mean, here you have the difference, and you also have that factor here. So this should rather tell you, oh, maybe this is the derivative of y. And then you look at these guys, and this C matrix here is the main reason why we did that crazy step. I mean, Lucas always said, this looks like a convolution operator, like really the convolution operator, like the integral version of that. Okay, so let's also treat W as a function. So here you have a convolution operator. This thing turns into an integral. I mean, okay, let's do that. Why not, right? So we have this functional equation. And now you can do the following thing. Maybe let's ignore this for the moment. So for the moment, let's assume that this function, I don't like it too much, right? It shouldn't matter too much. Let's assume it's a constant function. Okay, I don't know the constant already, but let's assume it's a constant function. So this is a constant expression. This is also a constant. Well, yes, this is also a constant value then. And now what you can do is you can take the derivatives of both sides. I mean, let's just do it, okay? I mean, let's assume y is differentiable. Then we end up with a differential equation that even I can solve, okay? Where gamma is some constant, I don't know exactly yet, okay? So that's great. That's great. So this gives us some idea what is the structure of y, right? And also it gives us some other very nice information, which is, again, we cannot turn it into a formal argument, but if you take that same equality here and instead of taking the derivative, you integrate both sides, then what you get, is this. You get that lambda, which is essentially our difference, just divided by 2 times the dimension, is 1 minus this integral. And if we assume that y is between 0 and 1, we see that this value here is at most 1. So which means that our lambda, I mean, whatever we do, we should not expect that it's getting bigger than 1. Okay? And this tells you in the end that that what you should get is a lattice width that is not larger than 2 times the dimension. But that's just a side comment. I don't want to confuse it too much. But this somehow gives us an upper bound. Anyway, okay, so I mean, what do we do here? Well, I mean, we solve it and we see that y should be some kind of an exponential function, right? Which was not clear from, I mean, it's not super surprising now, but like from the picture, there were tons of possibilities, right? So it's an exponential function. Okay, cool. So let's choose it as an exponential function where I don't know exactly what is the base. Okay, so we choose our vector. I mean, now we go back, right? Now we discretize things again. So let's hope that this works out, okay? So let's choose our vector A so that every entry, the ith entry is delta to the I minus 1 minus 1. So that we, like, we normalize it, right? So that the first entry is really 0. For some delta, okay? Actually, delta should be positive. And now it turns out that, I mean, this works out, okay? Because whatever delta positive you choose, you can use the previous lemmas and you can show that this is always going to give you a lattice-free simplex, d-dimensional, whose lattice width is this crazy expression. Okay, but what do we do now? Well, now that's easy. I mean, now we should certainly choose delta so that it maximizes that expression. And this is not so complicated. I mean, it turns out that you should choose delta as this thing here. Okay, so the base, of course, of that exponential function also, you know, contains d, and so you see that, man. I mean, just from the pictures, it would have been hard to see exactly that exponential function. But okay, now we have it. So you should choose this, and if you choose this, you go through just the previous, you plug it into the previous statement. And you see that the lattice width is in fact 2 times the dimension minus some lower order term. So it's square root, like this O of D here is square root of D basically. And that's it. That's the construction. So in particular, now we see that the flatness, like if the flatness constant is really linear in dimension, it's like the coefficient in front of D is at least 2. Okay, and yeah, I haven't, like, in all our computations, we have never seen anything that goes above 2 times d. I'm not aware of any object. I'm not saying that this is really the flatness constant. I mean, maybe it is. That would be spectacular. It would be great to really understand that construction better. Maybe try something with, like, not being simplices or anything. So I would be very happy to see some further progress in this and to understand how you can really construct large lattice-free objects. Okay, thanks a lot. That's it.